on air. I'm A.M. Grabelny, one of your hosts and a developer advocate here at AWS, joined by Nyla from NVIDIA. Nyla, please tell the audience all about you.
Hello, everyone. Thank you so much for having me. So I am Nyla Worker. I'm a product manager at NVIDIA for Omniverse Replicator. Replicator is a synthetic data generation framework for data for perception applications. So basically making computers see.
Now NVIDIA, very famous for its GPUs, obviously, but today we're talking computer vision and we're talking ML model training, specifically with computer vision. And you were educating me before we went live about actually some of the challenges that are specific to training computer vision models. Now, I let you know, I'm very unique. I have terabytes, just hundreds of thousands of terabytes of cat images. So I'm all set when it comes to building some computer vision models for cat detection. But you said oftentimes lots of companies, lots of people training models, they don't have access to as rich of a data set as I do.
Yeah, and I think you might be unique in your cat data set that might be very highly monetizable, selling a cat detector for all kinds of applications. But yeah, sadly, we don't have such a diversity of data sets for every application. Yeah, like we don't want to have data sets of 1,000 broken displays of a manufacturing line for like TVs or something like that. Hopefully not. That would be so wasteful.
Nyla, thank you, first of all, for recognizing how unique I am. I often say it all the time. But yeah, that's true, right? Like it's difficult getting some of these data sets. Some of these data sets don't even exist. Can you walk us through, before we even start getting into the data problem, what are some of the perception tasks that people are out there solving?
Yeah, so you can think of autonomous vehicles. The car needs to have an understanding of the environment around it, the cars that are in front, behind it. What is it that it's seen in front of it? Are there humans walking around? Is there a stop sign? Very important to have a stop sign detection, by the way.
Yeah.
But more unique, we might be able to get those data sets from just gathering data from the vehicle. But more uniquely, we have edge cases. So I drive a lot at night in California, and I every now and then see a deer, and I so hope that these cars can detect those deer.
Yeah. And that's a challenge when collecting those data sets, right? You don't know when a deer is going to appear. So it's difficult to go out and collect that data.
And you hopefully are not running around that many deers or like crashing into cars that much, you know?
Right. Very true. So yeah, that I think is a pretty unique problem to solve. You know,
but there is a lot more in the computer vision space. So let's talk about that too. So robots that are in a manufacturing line need to perceive where things are, like the things that are picking up. So like doing object detection to determine what is this and where it is in the frame. There might be more unique situations where you have a manipulator. So you want to detect where is this on the frame, but also the exact position of it. So like the pose of the object, X, Y, Z, and the translation and rotation over space so that it can successfully come in and grab it.
Okay.
So that's another perceptual task for which is actually very hard, like impossible to almost gather any real data.
Yeah, that makes sense. I mean, you're also working within a 3D space as well, right? So, flat images of, or like 2D images of a cat, they're not going to cut it for that type of problem.
Yeah, I don't think you have 3D captures of cats. Maybe you do, again, but maybe not nearly enough.
I have a little tiny motion capture suit for cats.
You made it just for cats, right?
I did, of course. Anyway, yeah, no.
That so is such a good point. Wait a second. Let's play with the toy example too.
Yeah.
Even if you are gathering data with like stickers or something like that to mark the pose of the object, you are actually disturbing the item. And that's not how it's going to be perceived in the real world.
That's a really good point. Yeah, I hadn't considered that. We also, I'm sure when dealing with data for computer vision models, some of these things, even if you can go get that data set, it's going to be cost prohibitive to do it, right?
Yeah. And especially so when the business motive is unclear. You think you could utilize AI for one use case that I'm thinking in logistics is determining where to send boxes. So this is a very expensive problem because if you accidentally send it to the wrong supermarket, now you've lost that inventory.
Yeah.
And it's your fault. So an idea there is to put a camera that can then detect what's happening in the space. But then you need to truly understand where to put that image, that camera, what camera to use, and then what exactly is going to solve your problem. Is it object detection, segmentation, or do you need to understand more of the space?
Yeah, that sounds really, really complicated. So you mentioned up top about Replicator producing synthetic data. What is synthetic data when compared to like these other data sets? What makes it synthetic?
Yeah, so I'm particularly speaking about synthetic data sets generated from synthetic 3D worlds. And the reason why it matters that this is generated to 3D worlds is because you might be able to generate 2D images. However, that does not solve the full lighting problem. So like you want to have a 3D representation in a world where you can modify lights. Maybe you can change the material, change the texture of the object, make it look more realistic or work in all kinds of lighting conditions. So a picture might not be able to capture all of those lighting conditions to begin with. So that's why we focus on generating or making 3D worlds from which you can then generate thousands of images that are actually parameterizable. So if you need to detect for darker environments, lighter environments, maybe you have pink light in your cat detection studio. Who knows,
Who knows? Who knows? That's true. Yeah, that's fascinating, actually. I mean, and it makes a lot of sense too, since physics is going to make a massive change on a lot of these properties, right? Especially, physics will be a key characteristic when you're doing something like autonomous driving, right? Like, so that makes a lot of sense to me too. So synthetic data is actually that's a really important point. I feel like it's generated within a 3D world that has the same rule sets that our world does.
Yeah, and like there we can have perpetual glaring afternoons.
Oh,
because
true.
glare is hard to use. It's actually where we see a lot of failure with cameras, and that's something that we can generate and then have more robust DNNs. Or for instance, maybe you are able to gather data from your production line, but you're only able to gather at a certain time of day, but turns out your manufacturing line is 24/7. So you encounter different light conditions and things like that.
Wow. So something that I know, I'm not an ML practitioner by any stretch of the means, but I've interviewed a lot of very smart people, and I've picked up some things along the way. One of the things I've heard time and time again when building ML models is that the iteration of an ML model is a lot of work and takes a lot of time, especially when it comes to the data, right? And even before you train the model, data preparation, data cleansing. And in this case, since we're talking supervised learning, data labeling is very time intensive for some of these non-synthetic data sets. How is that different with the synthetic data sets that Replicator?
Yeah, you touch a very good point. I used to be a distributed machine learning researcher at the University of Minnesota, and there I spent a long time getting very acquainted with ImageNet. And yeah, that's not the greatest experience to clean and like process data. But even that's an academic data set. That's much better than the clean data set, than the actual real world data set. So yes, most of your time in the real world data sets is going to be spent cleaning the data and like making it usable. But even once you've made it usable, you have a very fixed thing. You might be able to do that augmentation with a couple of augmentation techniques, But then, like, it's only hoping that you can get there. With synthetic data, though, if you train and it fails, you can regenerate the data set. And in fact, you must. This is like the one thing I'd like to make clear to ML engineers is like, if you get a terrible number with synthetic data generated from simulation, just change the parameters, change the light conditions, change the environment, and you're going to see an incredible performance improvement. So for instance, a project that I worked on where we were doing detection, at first we started with a very rough scene that looked not very realistic, and that failed. That we got 30% average precision with synthetic data. Then we made it look like a nice office space, and then we got about 50% average precision.
Oh, interesting.
However, then we randomized lights, because at the end of the day, the lights are changing over time. We actually noticed that the camera was had like different hues, the camera that was deployed in the field. So we randomized the lights. We randomized the wall textures, because it turns out that while in your synthetic world, you might have one color wall, in the real world, you might have a toddler that has drawn on the wall or that has made a mess in this environment. So randomizing the wall, randomizing certain things to the point that you force the deep neural network to learn the transferable things from the synthetic domain to the real domain. And what I like to, and by the way, this is an official technique called domain randomization. So what you do is you randomize the synthetic domain to the point that it encapsulates the real domain. And the DNN learns the things that transfer to reality, and thus you have a deep neural network that, while it was trained on completely synthetic data, it performs perfectly or like pretty well in the real world. I'm not saying it completely eliminates your need for a real data set. For knowing whether your DNN is performing, you need to test on a real data set. And for instance, for projects where we've done LiDAR, we've pre-trained with synthetic. We've gotten the network to converge much quicker after with real data. So even when you are not going to fully use synthetic data, it is very helpful at getting you 80% of the way there. And actually, with things like LiDAR point clouds, turns out humans are not great labelers.
Yeah, I imagine. I mean, it also sounds like a really great way to kind of engender the spirit of experimentation that goes with machine learning, right? I know it's incredibly important to know what outcome and what problem you're trying to solve when you set out to create a model. But sometimes people, want to see if they can solve a problem, but they just don't have any means of even testing out to see if it's feasible, right? Like you could probably iterate very quickly using some of this synthetic data to arrive at the conclusion of this is a feasible, ML problem or not, I would imagine.
Yeah, totally. And I think that's also where a lot of this research stem from. Like 6 degrees post estimation is something that you cannot get real data for. And a lot of the papers that came out exploring synthetic data were mostly because of 6 degrees of freedom or reinforcement learning. But it turns out that it just makes more sense to just use synthetic data to begin with, because at least with your synthetic 3D space, you have some reusability of what you build versus a data set that it takes months to gather and it might not really be useful at the end of the day.
Well, Nyla, I heard too that you've got some things to show us as well.
So I am going to show things around now. Okay.
All right. We can see your screen now.
Awesome. Okay, so I am in the documentation of Replicator. So here you are going to find in this link, which, by the way, you can find it by Googling Replicator, the documentation tutorials, and it will take you here. we have an overview, we have the exact API documentation, and then we have tutorials. And today I'm going to walk you through one of the tutorials that we have here.
Omniverse Replicator, I'm sorry, I didn't mean to interrupt, but Omniverse Replicator, full-featured SDK for generating this synthetic data, right?
Yes.
Okay.
So now you can come in and utilize Replicator, and actually all of Omniverse cool features to then create this 3D world and then generate that data set.
Okay.
So with that, I mean, Omniverse has incredible physics capabilities like Flex or some other physics particle simulation that you could use and then put it together with in your 3D scene and then utilize the API to generate synthetic data. And another thing that's really nice is Omniverse enables you to connect to multiple 3D tools like Unreal Engine, Unreal Engine, Maya, Max, and a bunch of other 3D tools that you can find in the documentation. So if you find any 3D assets in those tools, you should be able to import it to Omniverse, and then you should be able to use those 3D assets and 3D worlds to then utilize the Replicator API.
So then it's not just even creating that data set. You actually can then view the world itself that is being created.
Need to view the world itself. Yeah, exactly. So here we have the Replicator API in action. And this is a tutorial that you can go ahead and get started yourself. So the first thing that we do here is import Omni Replicator Core as Replicator. We create a new layer. This is a concept from USD, but basically it's like you've created a 3D world, and now we're going to add randomizations and the generation capabilities in a new layer. So in this case, we are also going to be creating the scene here. So we are calling a worker. So worker is, it comes with NVIDIA's characters. So NVIDIA provides you with a bunch of 3D assets so that you can go ahead and get started today. But if you had your own, you could have imported them and called them from here. So here I pass it worker, which is a person. I pass it props, which in this case is a bunch of vegetations. I pass it an environment, which in this case is a background full of puddles, and I pass it a surface. Then I define a function environment props, which what it does is it utilizes the props that we passed beforehand.
Right.
And it will instantiate them in the scene. And those instances, we then have their post modify. So that means that these assets are getting randomly put around in this scene based on the distribution that you put here. So here we're giving it a position and a rotation. Then we have the worker function where we're creating from USD the worker. Here is a very important piece for your code, which is we're giving it a semantic type. So here is where you are labeling this asset, this 3D asset. And now all of the data you get out of Replicator is going to have a perfectly labeled 3D asset.
It carries on that label to all of the different randomization.
Exactly.
That's awesome. That's really cool. And when we're talking worker, vegetation, these are all just 3D assets that you've created to bring in.
And I'm going to show them in a second, but
Awesome. I love seeing them.
But so the powerful thing here is you can see this is just one line, right?
Right.
And here we are going to be creating 10,000 frames.
Oh, there you go. So 10,000 iterations.
10,000 images.
Yeah. And they're all labeled automatically.
Yeah, with this class. Yeah, exactly. So that's like the cool thing is like you can automatically get labeled asset. There is a super awesome project from a dad that made a chair that follows a chair that is a robot that follows him around his backyard, so that his kid would sit in the chair and follow him. And the way that he trained it was with Replicator. He generated data infinitely, like enough data with Replicator for that.
That's hilarious. What does it actually look like?
Let me show you. But okay, yeah, just very quickly.
Sure.
Last important piece here is we're creating a camera. We have a whole camera tutorial that you can dive deeper into, but this is an important piece because you might have a different focus distance, you might have different camera parameters, and this is where you can modify it. And the API will walk you through how to modify that and match your camera parameters that you have in the real world so that your sensor is more true to reality. Lastly, we add a writer. So here we're basically telling it, get this writer from the writer registry, initialize this writer to this directory. So it's going to write the data here. And here we're telling it print RGB, print bounding box, but you could actually print a lot more data, which I'll show you in a bit. And then we attach this writer to the rendered product, which actually comes from that camera that you defined above.
Oh. Okay.
And then we start the randomization. So we tell it every frame, do 10,000 frames, and every frame randomize 75 of these props, randomize the position of the worker, and also modify the position of the camera.
Where the camera's focal point. Okay, interesting.
Yeah, we're not modifying the focal point, but the position of where the camera is.
Oh, like the physical. I see what you're saying. Yes.
Exactly. Yeah. So yeah, this is what that script does. And here we can see it running. This scene is quite a bit heavy and we're streaming, which is why I'm a little bit afraid that we're going to cut off. But basically you can see here all of those bushes being randomized in the scene and the person moving around in this scene. And all of this is getting stored to my output folder.
That's super cool. Now, I imagine this could be pretty intensive for some hardware. You know, are there options?
This on a laptop.
Oh, nice. I mean, like some of the more robust use cases too. You know, are there options for people that want to run this? You know, utilizing, you know, like cloud, you know, for example.
Oh, of course, yeah. So this is if you wanted to get like hundreds of thousands of images, or you wanted this to be much faster, right? That can only be done in the cloud. And that's where you would utilize a batch workload where we would we would copy that script and run it in a headless mode in the cloud. We actually have a tutorial in the Replicator documentation where we show how to utilize AWS with Replicator so that you can generate these 10,000 frames there. But yeah, so we have everything. You need it for your industrial use case, go and use the cloud, and you need to just explore. You can use it in a workstation at home. But yeah, for like a real end application, you would utilize the cloud.
I mean, that's still impressive though, just running on your own laptop. That's still like, you know, 10,000
but you would
images.
like to have it very fast, right?
Right. Yeah. Totally.
And the other thing is, this is a simple application. When we are talking about an autonomous vehicle, we're talking about 8 cameras, right?
Right. This is one camera.
Increases so much more. Yeah, this is one camera. This is a couple of assets. We're not talking about the synthetic city, right?
Right.
So that's where things get a little bit heavier.
Yes, that makes sense.
Okay, so
cool.
I've shown this tutorial and people are like, Nyla, great. This is cool, but we don't really need to detect humans in gardens all that much.
I see this as a huge problem. You know, how do we get people out of the gardens, right? Oh, no, I'm just kidding. No, we need to get more people in the garden.
Let me show you a video of this working and how we made it work in the real world, because I think that will be very powerful. So I'm sorry, all of you who want code, but this takes a little bit more time to build. But this is a real world use case of a robot that has been trained on synthetic data to detect the pose of this object. Wow. And actually, it wasn't only trained, like if you're using Isaac Sim, which is the robotic simulator, you could also test your control stack, which is what we did here. But basically, this robotic arm learned the pose of this object with synthetic data. As you can see here is the simulated environment of this robotic.
I saw that. That's another project from NVIDIA, Isaac Sim, when I was looking at the replicator docs. Really interesting. It's a robotics program, right?
Yeah, so Isaac Sim is the robotic simulator. Then we have Drive Sim, which is the autonomous vehicle simulator. And Replicator is used by both for autonomous vehicles, synthetic data generation, and also by Isaac Sim, which is robotics, synthetic data generation too, because that's one piece of the robotics workflow. And then it's used as standalone for industrial applications.
Well, Nyla, unfortunately, time has gotten away from us. It's just flown by. This is incredibly interesting to me. Thank you. I'm going to take your screen off here just for a second so people can see us fully. That was amazing. Really, thank you for coming on and showing us all of this. I heard you also have an upcoming conference. Before we leave, I want to give you a chance to talk about the GTC conference.
Yes, the GPU Technology Conference in March this year. Everyone should come. We have incredible announcements. And yeah, you'll get to learn a lot more about synthetic data, robotics, and so much more. Yeah, it's going to be cool. Every year I learned a lot during that conference. I strongly recommend everyone joins.
Nice. March 20th, I believe, right, is the date for that. And are you doing any talks?
I am giving a class on Replicator, so if anyone wants to join.
Okay, there you go. There's a reason to go to GTC, take the Replicator class.
Yeah, Nyla, there's also a couple of Isaac Sim classes, the talks that will be awesome, and Drive Sim talks. There's going to be a lot to learn from.
Okay, awesome. Go check it out. Thank you, Nyla, for joining us. I really appreciate it. And for everybody watching, go check out Replicator, go check out GTC conference, and stick around for more from AWS On Air. We'll be right back.
Take care. Have a good day. Bye-bye.